So today I will not, I will make a break, as I said, from physics, and I will try to address this issue of why society should invest in big science. I was a bit afraid of this talk, saying that, well, I'm taking some risks talking about this, but after having talked to some of you, I understood that I have no risk at all, because you indeed are probably as much addicted to science as I am. So this is the outline of the lecture. So I will start with some definitions, then I will say a few words about the science and culture, why pure science is useful. I try to bring a number of arguments here. I will talk about the relation between big science and technology development, and I will try to give you, if I think I will have time, to give an example of the impact on innovation, trying to quantify that impact. So I hope that you will get from here, even if you are already convinced that basic science should be done, that you may get some, for yourself, some arguments or some additional arguments that you can then use to try to convince other people. So we start with this question, that is a legitimate question. So when people hear to the price of big science experiments like the Large Hadron Collider or others like the Hubble Space Telescope, they wonder what are the benefits, and benefits that could justify that cost. Now, these projects are about basic science, so why is it worth doing? So it's a good question. Before trying to answer those, let me give you some definitions. What is this? What is basic science? So basic science develops information to predict and explain phenomena in natural world. It's different from what is called formal sciences. So these are matters concerned with formal systems like mathematics, logic, statistics. And then there are applied sciences, applying existing scientific knowledge to develop practical applications. So the typical examples are engineering and medical sciences. So fundamental physics, this is what we do at CERN and in other places, is recognized in philosophy of science as a fundamental science, and eventually more fundamental than other sciences like chemistry or biology. And these are, for that reason, they are normally called special sciences. So while fundamental physics looks for universal laws that are then normally expressed in mathematical language, special science include laws that, although accurate in normal conditions, they have exceptions. So they are not formalized in a precise language as mathematics, and so they have this characteristic of having some exceptions. So in a broad sense, fundamental physics is the analysis of nature conducted in order to understand how the universe behaves. So in this context, I will consider particle physics and astronomy, cosmology in the same package, if you want. So what is big science? Big science is a term that is used since the World War II, and this, as science progress, relied on large-scale projects, usually funded by governments or by intergovernmental agencies like CERN. So this was indeed a consequence of the development of important weapons and tools during the war. So in particular, radar and the atomic bomb. And so, in a sense, physicists took benefit from that, even if these applications, fundamental physics, so that implying building accelerators and telescopes in astronomy, they are not, or they were not related after the war with immediate military concerns. So now this went further, and towards the end of the last century, big science was applied not only to physics, but also and astronomy, but also to life science. So the typical example is the Human Genome Project. That is also a rather big project. Now, so this is this sets the stage for this. Now let us start to make some questions. Well, the first one, and some people sometimes ask me that, can we do this research without increasingly more powerful accelerators and telescopes? Why we are always running for bigger instruments? So when the proton synchrotron accelerator was built at CERN, it had a radius of 200 meters. It was considered it was in the 50s, a huge instrument. So it was certainly the last one that would be built with that dimension. So the question is, are there subtler ways to unveil the mysteries of nature? So we are getting more and more energy. Is not a better way to find things, to answer our scientific questions? Well, unfortunately, to the best of our knowledge, the answer to this question is no. For the time being, we don't know any other way to make this investigation. Now, maybe at least before some unexpected breakthroughs happen, this tendency will remain. So physicists will fight, or will try to justify the need to higher energy, to bigger telescopes. Technology will help, as it has helped in the past. So I think that I've told that during my career, the energy of the accelerators have increased by 6 orders of magnitude. And this was not only by making bigger instruments, it was because there was new technologies that allowed more powerful instruments to be built. So it's clear that there is research on accelerating technologies such that we can accelerate to the same energy in a smaller distance. And eventually we'll find ways to get to higher energies with machines that are not so big. But for the time being, we don't know. And we don't know if, in fundamental terms, there are other ways to search for, to understand the nature of matter. Now, the other question is that we can ask is, or that we ask, is it so big? So take a look at these numbers. So the European Union GDP in 2011 was 12.6 trillion euros. So for this matter, euro and dollar is the same. So the fraction invested in R&D in Europe, average over the countries, is of the order of 2%. So some countries invest more, others less. This is less than what the US invests, that is more close to 3% and 2%. But in Europe, and it doesn't matter if it's 2 or 3%, for the sake of this argument. So that means that the total expenditure per year in R&D is of the order of 250 billion euros. The CERN budget is 1 billion euro per year. So my guess now, what is the total particle physics R&D investment in Europe per year? So I put the factor 2.5 above CERN, and I say it's the order of 2.5 billion. This is my guess. Well, it could be a factor 2 higher. Well, if it doesn't change. I'm not here looking for factors 2. I'm looking for the order of magnitude. So if it is this, then 2.5 billion is 1% of the total R&D effort in Europe. It's 1%. So I think that at this level, we cannot argue that these big projects in particle physics are preventing other research fields to develop. There is still 99% to invest in life sciences, materials, whatever. So even if it is not 1%, if it is 2%, if these numbers are wrong, the argument stays. Now take a look also at these numbers. The cost of the LHC was 6 billion euros. So I've put 5 to make now numbers round. The construction time was 10 years. So the LHC cost per year was 500 million euros. That's the same number of millions of European citizens. That means that the LHC cost per year and per European was €1. The price of a coffee. So every European has contributed with 1 coffee per year to the LHC. It's really not much. And indeed, the LHC got contributions from other countries at an important level that I'm not accounting here. Now, other big projects in science. So this, I'm not completely sure of these numbers. They look to me reasonable. I've made some cross-checks at the type of numbers that are difficult to find. But so the estimations are that the Manhattan Project, so the atomic bomb, was $24 billion. Space projects integrated since 57 of the order of $100 billion. The International Space Station integrated over 30 years, eventually 100 billion euros. The Hubble Space Telescope, 10 billion. The LHC, 5 billion. So particle physics in this context is not so big. It's bigger than some of the telescopes that are being built, but there are more telescopes these days than accelerators. So, okay, but this is the order of magnitude of these projects. Now, what are the culture and say kind of philosophical arguments to do this research? I think that everybody agrees that humans feel enriched by knowledge about the periodic table, genetic codes, how the sun works, why the sky is blue, about the expansion of the universe. So we really feel good when we learn these things. Bob Wilson was the first director of Fermilab, was asked by a congressional committee, what will your Fermilab is so one of the main labs in the US for particle physics, so they had the Tevatron that was operating until recently. And he was asked, what will your lab contribute to the defense of the US? Nothing, he said, but it will make it worth defending. So I think that this notion is important. So knowledge in fundamental physics and cosmology is a major component of our cultural background, with its roots in Galileo, 16th century. So mankind as a whole should continue to explore this frontier of knowledge and can afford to do so. So this is what you think, and I think that also many people are interested by this. The number of TV shows, science magazines, blogs, etc. tells us that many people are interested in science. When Higgs was discovered and was announced in July last year, we estimate that there were 1 billion people looking to those news. So these are the number of viewers of a CERN video that was broadcasted by about 1,000 TV stations. There were, so in 4th of July, CERN retransmitted the seminar with the presentation of the results. It was a scientific seminar, but nevertheless there were about 500,000 connections, web connections to this seminar, to the webcast. We got 160,000 YouTube views of a CMS collisions animation. So So a short video of collisions animations that we have put in YouTube, and 17,000 news articles were written about the discovery in 180 countries. So this gives an idea of the interest in science. Now, another argument is to say that pure science is useful. So this is my next set of arguments. I will argue that the search for fundamental knowledge, motivated by curiosity, just by human curiosity, in particle physics, is as useful as the search for solutions to specific problems. So, now this brings the issue of the interplay between basic and applied research. And this interplay is quite complex. So it's a network of connections that is not easy to disentangle. Some people talk about the linear model, so we go from basic science, then there is applied science, then there is development of products, and finally they arrive to us. This model looks a bit too simplistic, and we have in science examples where the things went the other way around. George Porter said at some point that thermodynamics owes more to steam engine than steam engine owes to science. So thermodynamics is a main branch of classical physics. It was built upon results that to understand, if you want to how the steam engine works. Now, the other point in this relation is that the time scale involved in the different steps of these processes varies very widely, from several decades to several centuries. So it's very difficult to predict. Now, the other point is that technological revolutions are normally the most important, are associated to a change of paradigm. Now, I have here the example of the discovery and understanding of electricity that was purely motivated by curiosity, to understand what were sparks and so forth. So it turned out that electricity brought a technological revolution. So people could have investigated and have applied research on the candle to improve it, but they would not get the light bulb. So this is a comment by J.J. Thomson in a speech delivered in 1916. So this, you remember, he was one of the persons that discovered the electron. He said in that speech, "By research in pure science, I mean research made without any idea of application to industrial matters, but solely with the view of extending our knowledge of the laws of nature. I will give just one example of the utility of this kind of research. I mean the use of X-rays in surgery." So this was after at the time of the First World War. Now, how was this method discovered? It was not the result of a research in applied science starting to find an improved method for locating bullet wounds. Now, this method is due to an investigation in pure science made with the object of discovering what it is the nature of electricity. So remember, there was Thomson working with the cathode ray tube, trying to understand electricity, and then it was noticed that this tube was also emitting a radiation that is X-rays. Now, in the following slides, I will reproduce citations from Casimir. Casimir is a well-known theoretical physicist. He was at one time research director of Philips. And he made a number, so these are citations from him. About transistors. So one might speculate whether transistors might have been discovered by people who had not been trained and have not contributed to wave mechanics or quantum theory of solids. Now, it so happened that the inventors of the transistors were versed in and contributed to quantum theory of solids. So what the path here was from quantum mechanics in the 20s to a quantum theory of solids, to the invention of transistors, that allowed digital electronics, and then microelectronics implemented in large densities to IT industry. Can you imagine the economic value of quantum mechanics? Can you put a number? Now, about computers, one might ask whether basic circuits in computers might have been found by people who wanted to build computers. As it happens, they were discovered in the 30s by physicists dealing with the counting of nuclear particles because they were interested in nuclear physics. Now, this example illustrates the fact, repeatedly seen in history, that experimentation in basic sciences pushes the limits of technology, and this leads to new applications. Now, about nuclear power. One might ask whether there would be nuclear power because of the urge to have new power, and this would have led to the discovery of the nucleus. No. It happens that they were discovered in the 30s by physicists dealing... Sorry. What's that? I'm moving back. So it didn't happen that way. So I've mentioned in my first lecture how the nucleus was discovered by the experiments of Rutherford with alpha particles. He was trying to understand how the atom was built. Then people were trying to understand. They noticed, Marie Curie noticed the radioactive elements, transmutation between nuclei, and so on and so forth. So several people work on that. Certainly not to produce power. Now, some people have the idea that, well, when we have a problem, it is enough to put a bunch of scientists, clever guys together, well organized, and they will solve the problem. In the war, there was a big problem. So they did that, and it worked. So this gives the wrong impression. Indeed, it was an historical coincidence that the understanding of nuclear physics happened at that time, was happening at that time, making possible a nuclear bomb. But this was just a coincidence. Now, the other example of Casimir, about wireless telecommunication. In a urge to provide better communication, one might have found electromagnetic waves. They were not found that way. So they were found by Hertz, who emphasized the beauty of physics and who based his work on the theoretical considerations of Maxwell. So, and he concludes, Casimir concludes, I think there is hardly an example of 20th century innovation which is not in depth in this way to basic scientific thought. So, and this person was research director at Philips. So what are the lessons from these cases? First, the applications of new knowledge were highly profitable. No doubt about that. They were totally unforeseen when the underlying discoveries were made. There was a long time lag between the fundamental discoveries and their exploitation. In some cases, 1 century or more. Discoveries did not get rich. It's a pity, that part. Now, this is also the reason why funding of pure science should be so done by public funds. Fundamental science yield benefits which are not general, which are general rather than specific to individual products, and nobody can really. It's not possible to capture these benefits in a single company. So it's not really the kind of investment that should be done by private funds. Now, some people say, okay, very well. All this is very nice, but major benefits from such an esoteric science as particle physics cannot be imagined. Well, I think that this is a dangerous argument because it is too much arrogant about the imaginative power of the human mind. Our imagination, history shows that our imagination is somehow limited. So let's go back in history and try to put ourselves in the position in some centuries ago. Could they have imagined the future? And the answer is no. Research such as those cited by Casimir were regarded equally esoteric at that time. I have to use the right button here. So, because anyone in the 18th century decided to invest in understanding electrical sparks. I'm an investor. I look at the guy that is trying to understand the electrical sparks, and I have a sudden inspiration. I say, I'm going to invest in that because 1 century later, this will lead to the understanding of electromagnetic waves, and then to wireless telecommunications and cellular phones, and I will make a fortune. Now, imagine asking a researcher in the mid-19th century studying electrical discharges in gases and measuring the light emitted. What is the practical application of this research? The guy immediately answers, it may provide light bulbs for illumination. And it did. But this is easy to foresee. Maybe it's useful to understand electrical isolation. I have no idea if it really helped there. But no one could have guessed that these spectral lines were inspired Bohr's atomic model and the initial developments of quantum mechanics, which then led to solid-state physics, quantum solid-state physics, to the transistor, and to IT technology. Now, coming back more recently to particle physics, there was trying to answer to this argument that this is too esoteric to give any practical application. We had a near miss in particle physics. Now, if the muon, remember the muon, this kind of heavier electron is unstable, so it decays in electron and neutrinos. This particle was discovered in the 40s. Now, if the muon had a lifetime somewhat longer than it has before decaying, muons could be used to catalyze nuclear fusion, something that we are trying to do since many years as a hope for humanity to get energy and generate huge amounts of energy. Why this? Because the muon is 207 times heavier than electron. So if the muon is captured by a proton in what we call a muonic atom, then it forms a kind of hydrogen that is much smaller, is 200 times smaller than the normal hydrogen atom, because the muon is heavier. Now, this atom, of course, it exists during the time the muon exists. If it decays, the atom disappears. But if it stays there, it would be more stable and stay there without decaying more time. Two muonic hydrogen atoms would have an increased probability to fuse because the protons are much closer, would be much closer. So you know that fusion is trying to fuse isotopes of hydrogen, deuterium and tritium, into helium, and this makes energy, fusion energy. It's very clean. and it's a real hope of humanity. The problem is that to fuse hydrogen requires itself a large amount of energy, and we have to overcome so the electromagnetic interaction that is preventing the atoms to get closer. So another example, an application of antimatter. In the 30s, I told you, the positron was discovered. It was discovered by Anderson. And then later it was discovered that positrons are emitted from radioisotopes like fluor 18 or carbon 11. So these isotopes are versions of, of the nuclei of fluor or carbon that are not stable. So they have a different number of neutrons in the nuclei than the normal versions. And these ones, in particular fluor 18 and carbon 11, decay emitting a positron. They emit neutrinos and a positron. Now later it was found that this positron annihilates with the electron. And when the annihilation happens at rest, that means that the positron stops, finds an electron in matter, in normal matter there are plenty of electrons, and annihilates. And when it annihilates, what happens is that there are two photons that are emitted in opposite directions. Really opposite, back to back, and with the precise energy, 511 keV. Why 511 keV? Because this is the mass of the electron. What happened is that the mass of the electron and the positron that have the same mass was converted into the energy of these two photons. Why? How can we use this thing? Well, many decades after, this phenomena found an application in a medical imaging technique that is called positron emission tomography. So how it works, an atom of a positron emitter, be it fluor 18 or carbon 11 or other, is integrated by techniques of radiochemistry in a specific molecule called a tracer. Now this tracer is injected in the blood flow, and with the intention that these tracer molecules will bind preferentially with specific cells in the body, like cancer cells. So the main tracer that is used in positron emission tomography, that is called PET, for cancer diagnosis is FDG. FDG is a kind of a sugar with an atom of fluor 18 in their molecule. And this sugar is captured more efficiently by cancer cells than by normal cells. And so what happens is that you inject this in the body, and this tracer concentrates in the cancer cells. And then what you do is that you put detectors around, you detect these photons. So before that, the fluor 18 emits a positron, annihilation, two photons back to back, and many of these annihilations happen. Each time there is an annihilation, I see a line, because I see the two photons I have detected. Now I see another annihilation there, and another there, and another there, and all them intersect the same point. So that means that most of these annihilations are coming from the same source, the tumor. So then, with sophisticated mathematical methods, you can reconstruct a 3D image of the deposition of the tracer, of the distribution of the tracer inside the body. This is how the technique works. And it's being used for many, many things, and it's very powerful in terms of biomedical research, because it's what we call now a molecular imaging technique. You can develop tracers that bind to specific proteins or other molecules that you want to understand what is their role in the body. Now, about the speculations around the Higgs. The understanding, so I've told this should have been after, this lecture was planned after the next one. So, so I have not yet told what in the world is the Higgs. So, but so the Higgs has to do, I will tell you tomorrow, about the nature of vacuum. What is really the vacuum? And this issue, this question, has also to do with dark energy that Seth mentioned yesterday, why the universe is expanding. These things may be related, we don't know. But these may become one of the leitmotif for research in physics in the following centuries, to understand what is the vacuum. This may have enormous consequences. It is certainly unlikely that any application emerges within my lifetime. On the other hand, I have no idea where it will lead in the long-term future. So, what's the conclusion? Well, what's certainly sure is that it will not be possible to exploit laws and facts of nature that remain undiscovered. So if we don't work to discover them, for sure we will not be able to use them. And I'm convinced that basic research will be pursued as long as humankind remains an intelligent species. It's not given for granted. Now, practical reasons to invest in big science. Some people bring these reasons up front. I think this is a mistake. I think that we should not try to justify investments in big science with these practical reasons. They are important, they are quite important, they are relevant, but these should not be the main reason, for a number of reasons. Now, the first practical impact of these big projects is on education. Places like CERN, Fermilab, NASA and so on are packed with young people. These people learn new skills that later they will be using in industry. These students learn about physics, but not only. They learn about engineering, they learn about information technology, computers, software, hardware. They know language. They interact with all these people from different nations. They have to present their results in public. So they learn how to make highly complex systems that work reliably. And this is very important in industry for sure. So these people are a very valuable asset in any high-tech industry. Now, international cooperation is another practical aspect, impact of this type of research. This science is international. It brings people from many different countries. They tend to put aside differences, national differences, because these people are interested by science. During the Cold War, there were a number of Russian physicists working at CERN, and without problem. So everybody was working together in the same experiment without discussing too much about communism or capitalism. And the relations last and are carried over, in some cases, to industry and even to politics. It's very important, this aspect. Now, the development of high-tech industries. So to build these experiments or these accelerators requires new technologies, such as superconductors, cryogenics, large-scale computing facilities, etc. And many of these are subcontracted to private companies that develop new methods that then find application elsewhere. So this is known. This is the main argument that a politician normally uses to feel confident and reassure that he's making a good investment. But it's very hard to quantify the benefit from this. There were some estimates made at CERN that indicate that every euro that is paid to industrial firms in this type of contracts generates 3 euros of additional businesses for those industries. So take this as with with some care, these numbers may be wrong by some factor of 50% or even a factor 2. But there are many examples where we find this this multiplication factor. Now, to give some examples, now the other points are spin-offs. Spin-offs from accelerators. We develop technologies that then find applications in other areas. What are the spin-offs from accelerators? Accelerator technology, so the technology just to accelerate particles. There are some 17,000 accelerators in the world today. Out of these, only about 100 are used for particle physics or nuclear physics. So, where are these accelerators used? Where they are used for cancer therapy. They are used in semiconductor industry for ion implantation. They are used for electron beam welding and cutting, for sterilization, radioisotope production, the same radioisotope that then can be used, for example, in PET, for non-destructive testing, incineration of nuclear waste. So this is something that has still some promise to be fulfilled, but it's already being applied. It's also a source of synchrotron radiation and a source of neutrons. So you develop an accelerator just to produce synchrotron radiation. It's the radiation that is emitted when a charged particle is deflected. So the particle is being accelerated and radiates in a tangent to the trajectory, and then you have a beam of very high energy light, electromagnetic radiation, that can be used for a number of studies in biology, solid-state physics. A number of people are using this radiation, and also as a source of neutrons for other type of research. Spin-offs from particle detectors also exist. I've mentioned some detectors related to the LHC experiments in the second lecture. One of those were crystal detectors to measure electrons and photons. These crystals have found applications in medical imaging, in security, non-destructive testing, and in research. Multi-wire proportional chambers, that is another type of detector that was used in the outer layers of these big instruments to measure muons, have been used to design systems to inspect containers, so big detectors that you put outside to inspect containers. And there are other applications in semiconductor detectors, like in medical imaging. Now, spin-offs from informatics. There are a number of them. The most well-known is the World Wide Web. But there are also simulation programs that have been developed in particle physics that find applications elsewhere. Fault diagnosis, control systems, stimulation of parallel computing. I want to concentrate a little bit on the web. So this was invented by Tim Berners-Lee at CERN in '89 or so. So on the left here you have the first document that he produced, proposing a project, and this project then was accepted. And this on the right here is the first web browser. It's in the 90s. So info.cern.ch, and this is available in the CERN public site, so you can find it. And in this site you can read. Access to this information is provided as part of the World Wide Web project. The WWW project does not take responsibility for the accuracy of information provided by others, something that we are used to in the web. And it says then references to other information are represented like this. Double click on it to jump to related information. So this was really a nice idea, and that is now being used by many people. I would like to finish with a case that was the Tevatron case, showing the impact of technology and innovation developed for this Tevatron. Tevatron is a proton-antiproton collider in Fermilab near Chicago. So it went up to an energy close to 2 TeV, and it was the place where the top quark was discovered in '95. Now this is an analysis done by John Wormsley. Now, why do governments support science? Science allows us to understand things about the universe, but to make it we need money, and the government provides money. Now, science, these experiments have some side effects, and they give technological innovation, skills, education, the things that I have mentioned, and the governments take it and account for it. So in their balance, they see how much I have spent and how much did I get from these technological innovations. Unfortunately, in this graph, there is no an arrow that goes from this bubble here, understanding the universe, towards the government. This is what I've been discussing previously in the first part of this talk. But this is what we get. Now, the issue that John tried to answer is this one. Can we try to measure the payoff from the investment in the Tevatron? Payoff in terms of this technological impact. And he focused in 3 particular areas. PhD students, the impact on the superconductive magnet technology. So the magnets, the dipole magnets of the Tevatron are where? No, they are disassembled, superconductive. So this was the first machine in particle physics that was built using, at large scale, superconductive dipoles. So along the ring, fully along the ring. So previously, lab at CERN had used superconductivity, but only on the accelerator cavities. So the part of the ring that is responsible for the acceleration, not for the bending. And the third point that he discussed is the impact on computing technology, for reasons that I will discuss. Now, how much did it cost? So the Tevatron accelerator costed $120 million in $83. So in 2012, this means $277 million. Then we have to add the main injector project, because the accelerator doesn't normally need other type of smaller accelerators. And this is quite a lot, $450 million. Then you get detectors. You have 2 detectors, 500 million each, plus a number of experiments. The smaller detectors in the so-called fixed target program, 300 million. It accounts for the operation. So you say 20 years of operation of Tevatron, that's of Fermilab. So 100 million per year. So this represents 2 billion. So the total cost, he estimates for the Tevatron, $4 billion. Now, what are the credits? PhD students training. So the value of a PhD student is estimated at, in 2012 dollars, at $2.8 million by some entity that is supposed to be correct, or at least we suppose it to be correct. And the thing that we can estimate precisely is the number of students. So there were 1,400 PhDs made at the Tevatron. So if you multiply these 2 numbers, you get 4 billion. Now, superconducting magnets. So as I said, this was the first installation of mass-produced superconducting magnets on an industrial scale. Now, what is the current value of this industry, of the superconducting magnet industry, is 1.5 billion per year. The value of the magnetic resonance imaging, that is where you use superconductive magnets in large scale, is 5 billion per year. Now, we can say that this industry would certainly have succeeded anyway. They would certainly would get production of these superconductive magnets for magnetic resonance by themselves. So the claim here is that this activity at the Tevatron, the fact that this was done previously at the Tevatron, has accelerated this development. By how much? So let's guess, 1 or 2 years faster than otherwise. It's not much. 1 or 2 years to bring a large number, so thousands of these very complex magnets working and being produced reliably and so on, is a short time. If it was 1 or 2 years, then the financial impact would have been 5 to 10 billion. Now, I move to computing. So these experiments generate lots of data. At that time, in Fermilab, people had to develop, to push the computing power and the computing frontier to be able to process all that data. So they started, at that time we had PCs. Everybody remembers the PCs. So physicists for these experiments were the first to put PCs in racks. So we put 1 PC, 2, 3, many PCs. So now they sell the PCs, not the desktop, but PCs that already just slide into these racks. But at that time we started, for people I started with the desktop PCs. So these were called PC farms. So if I put 1,000 PCs, I get 1,000 times the computing power. And it was much less expensive than try to buy a supercomputer of some company. Now, these PC farms were running Linux, you know Linux, this operating system. Now, today, more than 90% of the world's supercomputers now use Linux, of these that are also computing farms, like Google and whatever. Now, distributed computing was initiated in particle physics at that time also in Fermilab, in the Tevatron, or related to that experiment. The concept was the concept of computing as an utility, and we called it the grid. So the web gives access to information. Here, the grid gives access to computing power. So I go to the grid, I submit a job to be executed, but it is executed in some computer. I don't know where, I don't care, I just care that I get back the results. Now, these grid resources were used for data analysis of the Tevatron experiments. Now we have cloud computing. So remotely accessible Linux farms are now commercially available. Amazon is providing some of these. Now, the value of the cloud computing industry today is 150 billion per year, so according to some estimation. Now, again, this industry would succeed in assembling these PC farms, but let's assume that this experience with these PC farms here at Tevatron gave an advance of 3 months, just 3 months in this development. The impact of 3 months is 40 billion. So the balance is then that people have invested of the order of 5 billion in the Tevatron, and in this 4 billion or 5 in terms of training of students, superconducting magnet, so pushing this technology and these Linux computing farms. The total benefit was 10 times more. So this is plausible. It's not totally unreasonable. I think that I went with some detail on these numbers, such that you can by yourself appreciate if these numbers are reasonable or not. I think they are. And so, also in terms of the technological impact of these big projects, this thing pays off. So I think that this was it, what I wanted to say. Just as final remarks, I think that I've tried to tell you that basic science has many basic motivations: human, philosophical, sociological, technological, economic. I think that the basic physics requires important resources, but they are not outrageously large. I think that our society can easily afford for it. On the other hand, scientists and science must be accountable to society. I think this is the best way to guarantee that we do good science. Okay, thank you.